Hello, my name is Truman Porter, and I will be presenting on multimodal transformers for detecting joint attention in parent-child interactions. We'll first start off with some background information, then establish the goals of the project, lay out my approach to solving these goals, go over some preliminary results, and finally conclude. Parent-child communication is critical. The communication in the beginning of childhood is very indicative of later development, and it is important to note that this is a unique style of communication. The way an adult speaks to a child is different from the way an adult would speak with another adult. It is also important to note that in the development of toddlers, they learn to communicate with gestures before they learn to communicate with speech. And the synchrony of speech and gestures in parents communicating with their children has been shown to improve the vocabulary of toddlers in later years. The goal of this project is specifically to analyze joint attention. Joint attention is an aspect of theory of mind. It's the idea that you can communicate about something that isn't actually present and share an idea of it. For example, if a parent wanted to tell their child about what a guitar is, they could use words to describe it, and the child would know what they were talking about without ever seeing the guitar. This aspect of communication is very useful because it is an indicator of autism spectrum disorder. Specifically, if a child lacks the ability to use joint attention, they are more likely to have autism spectrum disorder. For this study, we will be specifically analyzing the parent. This is because of how the data set is laid out, as well as the fact that the parent does play a critical role in the communication in parent-child communications. Existing analysis of children's communication generally relies on human experts, or it only uses one modality. So generally, a lot of the time, it only uses transcripts of speech, which leads to an inability to generalize to more diverse tasks. Some additional sub-goals of this project is to identify optimal features when analyzing communication. So we'd like to determine if there are features that are more individual agnostic, provide a lot of information about communication without giving too much information about an individual adult. For example, when we're comparing different audio-based features, is the acoustic information better, or is transcript-based information better? Are we getting more information from the actual tones being uttered and the pitch of them, or from the specific words and their sentiment? And there's a similar question for pose versus motion when speaking about gestures. For this project, we're using the ECOLANG dataset, which has 38 parent-child dyads. They're engaging in discussing familiar and unfamiliar objects and alternating blocks of those objects being present or absent in the room. You can see this in the figure on the right. They talk about different categories of objects, including tools, instruments, fruits, and animals, each in their own section. This means that we have 3 to 5 minutes per combination, with a total of 35 to 45 minutes per parent-child dyad. Some key annotations given by the ECOLANG dataset are utterances, which are essentially a transcript of the video broken up into distinct phrases and sentences, and the topics of those utterances are labeled as well. And we are also provided with gesture data, including when representational and manipulation gestures are given. Representational gestures are gestures that indicate physical aspects of an object being talked about, and manipulations are actually picking up that object and moving it around. Our approach is based on the paper Galeb et al., where we're going to use a transformer architecture to discover the nuances of how we can analyze these modalities. We first must prepare the features, the speech and gesture data from the video to be fed to the model. We then pre-train the model to give it an ability to understand communication and to some extent. Next, we fine-tune the model, meaning we ask it to perform that classification task of detecting joint attention. Finally, we evaluate that model and compare the results between different modalities. So for example, if we only gave it speech, how does it compare to giving it speech and text? And comparing the accuracies of these different combinations will allow us to see how much the combination of speech and gesture contributes to the model's understanding. The features that we are currently giving to the model are key points from the video data. So we look at each individual frame of the video and extract 2D coordinates of key joints, including elbows, shoulders, etc. And we select a subset of the key points provided by the VitPose model to hopefully provide a robust communication of gesture data. We also use the MEL frequency cepstral coefficient as a representation of audio data. Specifically, it's intended to provide the data in a way similar to how humans interpret speech. This technology is used for things like voice transcription, so we thought it may be a useful way to represent that audio. In actually training, we start with that pre-training task, and we ask the model to predict, given the 3 previous seconds of communication, what the next pose and the next phrase that's said are. To validate that the model's actually learned something general, we test it on a distinct set of adults that wasn't seen in the training set. We do a similar thing for the fine-tuning, but we switch the task to being that binary joint attention detection task. And we only focus on windows that contain utterances because we believe they're more information dense. We again validate on disjoint pairs and test different classification heads to compare their performance as well. The results show that across 10 cross-validated folds, the model unfortunately does not perform better than a baseline of simply guessing true each time. This is an unfortunate result, but it is not in any means ending the project. We see promise in this method of analyzing, and so we plan to continue. So while our current architecture isn't functional at our scale of data, we would like to identify a larger data set to test again, see if it's just simply individual overfitting causing the model to not work well on a more general audience. Additionally, we would like to test out those more individual agnostic features I was talking about before. So try maybe using the transcript instead or other features like that. In addition, we'd like to compare additional modality options. So I've talked about speech and gesture, but there's also things like facial expressions, the emotion, and other things like that are conveyed by the face, and prosody, which are non-verbal elements of speech, such as rhythm, staccato, etc. And we would also like to investigate the combinations of modalities once the model is performing better than baseline. Thank you. Are there any questions?
Okay, can you return to slide 5? Okay, so I want to know a little bit more about why you chose this ECOLANG data set specifically.
Yeah, so the first month of this research was sort of focusing on what data do we have to address late talking or autism spectrum disorder related issues in children. And unfortunately, there aren't that many data sets that contain videos of children. This is largely due to the privacy issues and the ethical issues that come with these kinds of data sets. We identified a few, but this was the largest one we were able to find that was both quality and accessible to us. So we landed on this, but we're hoping to find larger data sets in the future.
How can a transformer model understand communication?
So a transformer model works by identifying patterns in time series. So you can see this maybe better in large language models such as ChatGPT. When it's looking at a sentence like the quick fox jumped over the dog or whatever, it's seeing like, okay, this is a common phrase, I'm recognizing patterns in this. So of course at the end, like dog would go there. In speech, though, and gesture, we can say, okay, if someone's nodding their head, they're more likely to say yes than they are to say no. And so it's picking up on these patterns, and through picking up on those patterns, it's having a representation of the data in its sort of memory that it has, allowing it to, in some cases, represent semantic or other information.
For that pre-training task, you talked about how you had it look at the last 3 seconds and then predict the next bit. Could you talk a little bit about why you chose 3 seconds for that sliding window?
Yeah, so there was a couple reasons we chose this length of time. One is we wanted to constrain the amount of time the model had, because otherwise, the larger the model, the larger the length of time you have, generally the more data you need in order for it to pick up on relevant patterns. In addition, the previous research I talked about, Galeb et al., they used a 3-second window, and when looking at the windows of utterances, they gave specific time lengths of when the utterance was said, and 95% of those fit within that 3-second window. So we figured it was a good amount of time to constrain it by.